So I'd like to do some examples of our main theorem involving asymptotics. To recap what we said in the previous video, let f be a function that has coefficient of x to the n given by the constant an. If these two conditions hold, then there's a nice asymptotic formula for those coefficients. So let's do an example and see how this is used in practice. So let's suppose a of x is the generating for my sequence, n going from 0 to infinity, of an x to the n. And let's suppose that's equal to 1 over 1 minus 3x times 1 plus 2x. Now, we actually have seen this example earlier in the course. This was a generating function we found by playing around with a recursion. And it turned out that when we solved this by splitting this into two terms using partial fractions and expanding each term as a geometric series, we found already that an happened to be 1/5 3 to the n plus 1 power plus minus 1 to the n, 2 to the n plus 1 power. So that was a result we had earlier in the course. But now let's look at this generating function and apply our new machinery and see what happens. Now, condition 1 says you need to be identifying the singularity with smallest complex magnitude. You want to find the singularity of this function that's closest to 0. Otherwise, this approach won't work because condition 1 won't hold. So if you look at the singularities of this function, I have division by 0 and therefore singularities at 1/3 and negative 1/2. So I have singularities at 1/3 and negative 1/2. 1/3 is smaller in absolute value than negative 1/2. So that is going to be my R value in this theorem. The alpha value that is in this theorem is going to be 1, because we see that if I take this function a of x and I multiply by 1/3 minus x, so 1/3 minus x times a of x, this actually can be simplified, because this, I believe, if I rewrite the bottom function, so if I factor 3 out of here, I will get 1 over 3 times 1 plus 2x. So when I multiply by this, here my R is equal to 1/3, my alpha is equal to 1. I've removed the singularity at 1/3. What remains is a generating function that has smallest singularity at negative 1/2, which is farther away from 0 than 1/3. So we have the limit as x goes to 1/3 of 1/3 minus x to the first. A of x is equal to, so now I can just plug in 1/3 in here for x. There's no issue anymore. And I believe when you do, you get 1/5. So therefore, what we have is an, the coefficients of this generating function, is asymptotic to c. In this case, c is 1/5. It's the result of this limit. So I have 1/5 n to the alpha minus 1 power. So alpha is 1 in this example. So I have 1 minus 1 divided by gamma of 1 times r, which is 1/3 to the n plus alpha, n plus 1 power. And if you simplify this a little bit, gamma of 1 is 1, n to the 0 power is 1. I believe you get 1/5 3 to the n plus 1 power. That matches what I was hoping to get originally, because we've seen in our past that this is the actual coefficient of an. And from there, I can tell that the dominating term in this expression is 3 to the n plus 1 times 1/5. That's more powerful than this 2 to a power. And so therefore, I do get an asymptotic result that checks with my previous knowledge. Okay, let's do another example in this video. How about this? Let's combine our ability to find generating functions using the exponential formula together with the asymptotics examples. So here's a question. What is the probability that a permutation of n has no cycles of size 1? This is known as the derangement problem. So if a permutation happens to have no single cycles of length 1, then the term for this is a derangement. Okay, this is the perfect setup for the exponential formula because I'm thinking about permutations and their cycle structure. The cycles are the cards in the hand. The hand is the total permutation of n. So using the exponential formula, I have the generating function n going from 0 to infinity, where I'm counting the number of permutations sigma with no 1 cycles. We stated the exponential formula as a bivariate generating function with both x and y. I'm taking y to be 1 to just get a straight count of the permutations with this property. So I'm counting permutations with no 1 cycles times x to the n over n factorial. That is equal to e to the 1 times the sum n going from 2 to infinity of x to the n over n. I got this because of our previous experience counting permutations and cycles using the exponential formula. I know that the number of cycles that you can create, the number of ways that you can create a single card with n integers, so a single cycle with n integers in it, is n minus 1 factorial. So when I put the n minus 1 factorial into the generating function and divide by an n factorial, I simply get what you see here. So we've done examples like that in the past, so I kind of did this one more quickly. I recognize this sum as e to the log 1 over 1 minus x, but without the first term. So this series that we've seen before in our past is the sum if the sum started at 1. So I don't have the first term. So here's my generating function. This is equal to e to the log power. E and log are inverses. So if I split the e into 2 pieces, I get e to the negative x divided by 1 minus x. Now, the coefficient of x to the n in this generating function answers my question, because I'm getting the number of permutations without any cycles of size 1, and I'm dividing by n factorial. N factorial is the total number of permutations in all of any permutation of n whatsoever. So when I take this and divide by n factorial, I am getting a probability. I'm getting the total number divided by, the number of permutations with my certain property divided by the total number of permutations. So I'd like to understand the coefficient of x to the n in this expression. That's the answer. And this expression is perfect for our asymptotics ideas. Our asymptotics ideas tell us to look for the singularities of this function. So this function has a singularity at x equals 1. You can't plug in x equals 1 because then you'd be dividing by 0. And that's really the only singularity of this function whatsoever. So this has a singularity at x equals 1. So I'm going to take r equals 1 in this example. And we see that the limit as n goes to infinity of, excuse me, not n goes to infinity, x goes to 1 of 1 minus x times my generating function, e to the negative x over 1 minus x. This totally cancels. I could just take the limit as x goes to 1 of e to the negative x, and I get e to the negative 1. So this is my constant c in the statement of our main asymptotics theorem. R is equal to 1. This R in the theorem is 1. And alpha is also equal to 1. So R is 1, alpha is 1, and C is e to the negative 1 power. So thus the answer is asymptotic to C, which is e to the negative 1, times n to the 1 minus 1 power, alpha is equal to 1, divided by gamma 1 times 1 to the n plus 1 power, which is simply equal to e to the negative 1, which is equal to 1 over e. So that's a famous result that we got pretty quickly using our asymptotics results. Now, an alternative method, if you're interested in getting this result, is to actually explicitly write this out as the product of two functions. So this is the product of 1 over 1 minus x times e to the negative x. You could expand both of these as series and multiply. You can get a similar result, but I chose to use our new machinery. I'd like to do a number of more examples of the asymptotics theorem in follow-up videos. Please follow me along there.